My name is Firas Awad. Our presentation topic is atomic clocks, and I will open the presentation with a definition. Atomic clock is a clock device that uses an electronic transition frequency in the microwave, optical or ultraviolet region of the electromagnetic spectrum of atoms as a frequency standard for its timekeeping element. Atomic clocks are the most accurate time and frequency standard known, and are used as primary standards for international time distribution services to control the wave frequency of television broadcasts and in global navigation satellite systems such as GPS. The principle of operation of an atomic clock is not based on nuclear physics, but rather on atomic physics and using the microwave signal that electrons and atoms emit when they change energy levels. Early atomic clocks were based on masers at room temperature. Currently, the most accurate atomic clocks first cool the atoms to near absolute zero temperature by slowing them with lasers and probing them in atomic fountains in microwave-filled cavity. An example of this is the NIST atomic clock of the US National Primary Time and Frequency.
The accuracy of an atomic clock depends on the two factors. The first factor is temperature of the simple atoms. Colder atoms move much more slowly, allowing longer probe times. The second factor is the frequency and intrinsic width of the electric transition. Higher frequencies and narrow lines increase the precision.
Hello everybody, I am Bilal Jibrin. The idea of using atomic transition to measure time was first suggested by Lord Kelvin in 1879. Magnetic resonance developed in the 1930 by Isidore Rabi became the particle method for doing them. In 1945, Rabi first publicly suggested that atomic beam magnetic resonance might be used as the basis of a clock. The first atomic clock was an ammonia major device built in 1949 at the US National of Standard NBS, now NIST. It was less accurate than existing quartz clock, but served to demonstrate the concept. The first accurate atomic clock, a cesium standard based on a serotine transition of the cesium-133 atom, was built by Louis Eisen in 1955 at the National Physical Laboratory in the UK. Calibration of the cesium standard atomic clock was carried out by the use of the astronomical time scale in fire time ET. This led to the international agreed definition of the latest SI second Beijing based on atomic time. Equality of the ET second with the atomic clock SI second has been verified to within 1. But in 1010, the SI second, this inherits the effects of the decision by the originally designer of the ephemeris time scale, determining the length of the ET second.
Hello everybody, I am Muhammad Jondi.
Since the beginning of development in the 1950s, atoms clock have been based on the hyperfine transition in hydrogen 1, cesium 133 and rubidium 87. The first commercial atomic clock was the atomic chron manufactured by the National Company. More than 15 were sold between 1956 and 1960. This bulky and expensive instrument was subsequently replaced by much similar rack-mountable devices such as the HP model 1516 cesium frequency standard released in 1964. the late 1990s, four factors contributed to major advances in the clocks. Chip-scale atomic clocks, such as this one unveiled in 2004, are expected to greatly improve GPS location.
Hello everybody, my name is Muhammad Shakar and I will talk about definition of the second. Under the International System Units or CIBM units, since 1967 the second has been defined as the duration of 919-263-1770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the Ca-133 atoms. In 1997, CIBM added that the period would be defined for calcium atoms at rest and approaching the theoretical temperature of absolute zero. And in 1999, it included corrections from ambient radiation. Absolute zero implies no movement and therefore zero external radiation effects. The second, thus defined, is consistent with the Empress second, which was based on astronomical measurements. The realization of the standard second is described briefly in a special publication from the National Institute of Standards and Technology and in deal by the National Research Council of Canada. The components: cesium source, 2 magnets, 2 getter, Ramsey cavity, hot wire CS ionizer, ion collector, vacuum pump, and amplifier, and servo control and quartz oscillator.
Hello everybody, I am Muhammad Abu Ghayada. I will be talking about the atomic beam standard. The atomic beam standard is a direct extension of the Stern-Gerlach atomic splitting experiment. The atoms of choice are heated in an oven to create gas, which is collimated into a beam. This beam passes through a state selector magnet A, where atoms of the wrong state are separated out from the beam. The beam is exposed to an RF field or near the transition. The beam then passes through a space before it is again exposed to RF field. The RF field and a static homogeneous magnetic field from the C field coil will change the state of the atoms. After the second RF field exposure, the atomic beam passes through a second state selector magnet B, where the atom's state being selected out of the beam at the A magnet is being selected. This way, the detected amount of atoms will relate to the ability of match the atomic transition. After the second state selector, a mass spectrometer using an ionizer will detect the rate of atoms being selected or received. Modern variants of the beam mechanism use optical bumping to transition all atoms to the same state rather than dumping half of the atoms. Optical detection using scintillation can also be used. The most common isotope for beam devices is cesium-133Cs, but rubidium-87Rb and thulium-205Tl are examples of others used in early research. The frequency errors can be made very small for a beam device, or predicted in such a way that a higher degree of repeatability and stability can be achieved. This is why an atomic beam can be used as a primary standard.